Hey fellow nerds, let us continue our discussion on Opamp applications. Today we will cover comparators and their applications as a level detector, a zero crossing detector, a window detector, a multi-level detector, and a time marker generator. Let us start with a non-inverting comparator. This is what a comparator basically does. It compares a signal voltage with a non-reference voltage. To build a non-inverting comparator, let us take an op-amp. Open loop gain is infinite, so we have an ideal op-amp. We'll give the input to the non-inverting terminal through a resistor like this. At the inverting terminal, we will give a reference voltage. The most important point here is there is no feedback loop. We are not feeding the output back to the input. Since the op-amp is in open loop condition, effective gain of this circuit will be the original gain of the op-amp, which is infinite. Let us see what happens when the input is greater than the reference voltage. In any case, output will be differential input multiplied by the gain. Here the differential input will be Vin minus Vreference. Gain is infinite. So output has to be Vin minus Vreference multiplied by infinite. We took the condition Vin is greater than Vreference. So Vin minus Vreference will be positive. The output cannot be infinity, so it will be at the positive saturation voltage. Now let us see what happens when input is less than Vreference. Again, output will be differential input multiplied by the gain. But this time, Vin is less than Vreference, so Vin minus Vreference will be negative. Since output cannot be negative infinity, it will be negative saturation voltage. That means whenever input is greater than the reference voltage, output will be positive saturation voltage. Whenever input is less than reference voltage, output will be negative saturation voltage. Let us take a sinusoidal input signal and try to plot the graph. Before that, we have to set a reference voltage. Let it be here. Every time input is greater than the reference voltage, output should be positive saturation voltage. Every time input is less than the reference voltage, output should be negative of the saturation voltage. If we plot it, this is how the output will look like. You can see that every time input crosses the reference voltage, state of the output changes. Let us take another graph. Take differential input voltage on the x-axis, output voltage on the y-axis, and plot the transfer characteristics. We saw over here that whenever the differential input voltage is positive, output is plus Vsat. Whenever it is negative, output is negative Vsat. So the transfer characteristics will look like this. Let us now see different methods of providing the reference voltage. The first one is the simplest. We'll use a DC battery. Let's take the comparator circuit and connect a DC battery at the reference node like this. Clearly in this case, the reference voltage will be equal to V. The second method is to use a zener diode. Let's take the comparator circuit and connect a zener diode like this. We know when the zener diode is in breakdown region, it will have a constant potential across it, and obviously it can be used as a source of reference voltage. But does this work like that? We know no current can flow in or out through the input terminal because an ideal op-amp has infinite input impedance. That means no current will flow through the diode and it will never be in the breakdown region, and we can never use it as a reference voltage. So this is not how we connect it. Instead, this is what we do. We will connect this point to VCC. We will connect this point to plus VCC through a resistor like this. Now, since we have plus VCC here, a positive potential will be dropped over here, making the zener diode reverse biased. When it is reverse biased enough, it will have a potential Vz across it. A current Iz will be flowing through it in this direction. Now we can use this as a reference voltage. The potential at this point will always be Vz. So the reference voltage we provide will be Vz. Also, now that you understand how the reference is taken, let me redraw the circuit in a bit different way like this. So that input is on the left side, output is on the right side, and everything else is in between. The next method is to use a fixed voltage divider. we'll take the comparator circuit. From VCC, we will build a voltage divider like this. VCC will be divided between R1 and R2. We will connect this point to the reference node. Now reference voltage will be whatever is the potential that drops across R2. So we can write reference voltage is VCC divided by R1 plus R2 multiplied by R2. Before we move on to the next method, let me redraw this circuit also, the same way we did the last one. The next method is to use a potentiometer or a variable resistor. Let's take a comparator circuit, take a potentiometer and make a connection like this. Let's take the resistance of the upper part to be RA and the lower part to be RB. Whatever potential we get at this point will be the reference voltage. The potential here is still taken from VCC. So in this case, V reference will be VCC divided by RA plus RB multiplied by RB. This is again a voltage divider, but this is not fixed. Now that you understand the connections, let me redraw the circuit like this. These are not the only ways of giving a reference voltage. Sometimes it can come from the output of another circuit. But the idea remains the same. Input voltage is being compared with a non-reference voltage. Let us now make an inverting comparator. First, we'll take an Opamp. Since we need an inverting comparator, input will be given at the inverting terminal. Reference will be given at the non-inverting terminal. Let us use a voltage divider. The connections are clear, so let me redraw the circuit in a way that eases my brain. Again, we don't have a feedback loop, so gain is infinite. Let us see what happens if input voltage is greater than the reference voltage. We know output is the product of differential input voltage and the gain. Here the differential input voltage will be V reference minus V in, and gain is infinite. V in is greater than the reference voltage, so V reference minus V in will be negative. Since output cannot be negative infinity, it will be at negative saturation voltage. Now when input is less than the reference voltage, V reference minus V in will become positive, and so the output will be at positive saturation voltage. Let's take a sinusoidal input signal and plot the output. But before that, we need a reference voltage. Whenever input is greater than the reference voltage, output will be negative Vsat. Whenever it is less than reference voltage, output will be positive Vsat. The output will look like this. You can see that every time the input crosses the reference voltage, output switches its state. Let's take another graph. Take the differential voltage on the x-axis and output on the y-axis to plot the transfer curve. It will still look the same. Why? Because even now, when differential voltage is negative, output is negative Vsat. When differential voltage is positive, output is positive Vsat. So both non-inverting and inverting comparator have the same transfer curve. Let us now learn some applications of comparators. The first one is a level detector. It detects whether an input signal is above a particular voltage or below it. For that, we need an Opamp. Let's give the input at the non-inverting terminal. I'll take a voltage divider for the reference voltage and connect it to the inverting terminal. This is the same circuit that we just discussed. All it does is give positive Vsat at the output if V input is greater than reference voltage and give negative Vsat at the output if input is less than reference voltage. All we are going to do is connect an LED at the output like this. Now, when input is greater than the reference voltage, LED will be on. And when input is less than the reference voltage, LED will be off. Let us also take a look at the inverting version of this, but before that, I want to redraw the circuit. To make the inverting version of this, we'll take an inverting comparator. Now, connect an LED at the output. This is it. Now, whenever input is greater than the reference voltage, LED will be off, and when it is greater than the reference voltage, LED will be on. Let us now make a zero crossing detector. This is actually pretty easy because it is a basic comparator with reference voltage being 0. All we have to do is take an Opamp. Assuming we want a non-inverted version of it, connect the input at the non-inverting terminal and ground the inverting terminal so reference voltage is 0. Now, when input is greater than the reference voltage, which is 0, output will be plus Vsat. And when input is less than 0, output will be negative Vsat. If we take a sinusoidal input signal and plot the output, it will look like this. Since the reference voltage is 0, output will change its state every time the signal crosses 0 volt. Let us now make a window detector. A window detector detects whether a signal is between two values. For that, we need two op-amps, A1 and A2. For A1, we'll give the input at the inverting terminal. For A2, we'll give it at the non-inverting terminal. We basically only have one input signal, so we can show it like this. Now, for reference voltage, we'll take a voltage divider between plus VCC and ground. But this time, we will have three resistors, R1, R2 and R3. For the first op-amp, we'll take the reference voltage at this point. For the second one, we'll take it over here. VCC is being divided between R1, R2 and R3. Out of that, whatever is dropped across R2 and R3 is V reference 1. So V reference 1 is VCC divided by R1 plus R2 plus R3 multiplied by R2 plus R3. Again, VCC is being divided between R1, R2 and R3. Out of that, whatever is dropped across R3 is V reference 2. So V reference 2 is VCC divided by R1 plus R2 plus R3 multiplied by R3. Finally, output will be taken together from both op-amps. Now let's take a table and see if this works. In the first column, we'll take the input levels. The first case is when input is greater than the first reference voltage. Second one is when it is between the two reference voltages. Third one is when it is less than the second reference voltage. In the second column, we have the output of the first op-amp. In the third column, we have the output of our second op-amp. Finally, we have our final output. Let's take the first case. Input is greater than the first reference voltage. The first comparator has input in the non-inverting terminal. So when input is greater than the reference voltage, output will be 0. The second comparator has input at the non-inverting terminal. So when input is greater than the reference voltage, output will be plus VCC. Here input is greater than the first reference voltage. Obviously second reference voltage is less than that. So input has to be greater than this value. That means here the output will be plus VCC. Now take the second case where input is between the two reference voltages. Let's take the first comparator, which is inverting. Input is less than the first reference voltage. Since the comparator is inverting, output will be plus VCC. Now input is greater than the second reference voltage. So for the second comparator, which is non-inverting, output will be plus VCC. Now in the third case, input is less than the second reference voltage, which means input is obviously less than the first reference voltage. So for the first comparator, which is inverting, input is less than the reference voltage, so output will be plus VCC. For the second one, which is non-inverting, input is less than the reference voltage, so output will be 0. Now comes the problem. We have shorted the outputs of these two. Forget about the second case. We have plus VCC as both outputs, so probably the final output is also plus VCC. But what about this and this? In the first case, here we get 0, here we get plus VCC, then what is the output? Can we really short these two outputs? To understand how this works, we might have to get inside the op-amp a little bit. Also, before we do that, we'll have to add a resistor over here to VCC. You must have noticed, instead of taking plus VCC and minus VCC, this time I have taken plus VCC and 0 for both op-amps. And that is perfectly fine. The supply rails don't have to be equal and opposite all the time. All they do is just decide how far the output can swing. Since we used plus VCC and 0, the output of this circuit can only swing between 0 and plus VCC. That's all the difference that it makes. Now, I said we'll go inside the op-amp, but we won't go any deeper. We will quickly look at what's actually happening inside the op-amp's output stage. Op-amps can have different kinds of output stages. For a window comparator, we will use an op-amp with the open collector type. Here, a bipolar junction transistor will be used as a switch. This much is inside the op-amp. This is the external resistor we connected between the output and VCC. I said the transistor is being used as a switch. The idea is very simple. We will get some input at the base of the transistor. We know for IC to flow, VBE should be greater than 0.7 volt. So when we have enough potential at the base of the transistor will be switched on and collector current will flow like this. If it is not enough, there will be no collector current. Let us mark the collector current. Now let me explain to you how this will affect our final output. We know when transistor is on, IC will be flowing through the resistance RL. That means potential will drop across RL. The potential drop will be equal to IC RL. Now, if this is equal to plus VCC, then what will be V out? Out of plus VCC, all of it will be dropped across RL and V out will be 0. If the transistor is on, IC flows through the load resistor and all of VCC drops across RL, which means final output will be 0. The same way, if transistor is off, then IC will be 0, which means there is no potential drop across RL. So we have plus VCC here. None of that will be dropped across RL, which means V out will be equal to VCC. Or we can say the output voltage is pulled up to plus VCC by the resistance RL. Using that idea, we call this resistor the pull-up resistor. Now before you forget, let me remind you again. Our problem was that we wanted to short the outputs of two op-amps. How does an open collector output help us do that? To understand that, let us take the open collector output stage of two op-amps and connect the final output together. Note that we only have one pull-up resistor. Let's take a table and see if this works. We can have 4 different cases. When Q1 is off but Q2 is on. When they are both on. When Q1 is on but Q2 is off. When they are both off. Let's take the current flowing through RL to be IL. Now take the first case. Q1 is off, which means its collector current is 0. But Q2 is on, that means it can have a collector current. So current can flow through RL because it does have a path through which it can go to the ground. And that means in this case, potential will drop across RL and V out will be 0. In the second case, both are on, which means again the current through RL can go to the ground, just that now it has 2 paths to do so. Again potential will be dropped across R and V out will be 0. In the third case, since Q2 is off, no current can flow through Q2, but still IL has a path to go to the ground through Q1. Again V out will be 0. Now in the final case, both are off, which means collector current for both these transistors are 0. There is no pathway for current through RL to go to the ground, which means no potential will drop across RL and V out will be equal to VCC, or RL pulls up V out to plus VCC. To make this more clear, let us go back and see this relation. When transistor is on, output will be 0. When transistor is off, output will be VCC. That means when Q1 is off, op-amp A1 will have an output plus VCC. And when it is on, Opamp A1 will have an output 0. Let's add two more columns to show the outputs of A1 and A2. Now forget these two columns. We don't care about what is happening inside the Opamp anymore. When output of A1 is plus VCC and A2 is 0, final output is 0. When outputs of A1 and A2 are both 0, output is 0. When output of A1 is 0 and A2 is plus VCC, output is 0. But when both outputs are plus VCC, output is plus VCC. Isn't this just an AND gate? Let's go back to our original circuit and apply what we learned over here. When the two outputs are shorted, it simply works as an AND gate. That means we can easily fill this table now. 0 plus VCC, 0. Plus VCC 0, 0. Only when both op-amps give plus VCC, output will be plus VCC. And this means the circuit will detect whenever the input is between the two reference voltages. Let us now take a triangular input signal and plot the output. But before that, we need two reference voltages. The output should be high only when the input is between these two values. Let us plot the graph. This is how it will look like. Let us now redraw this circuit also in a way that input is on the left side, output is on the right side, and everything else is in between. Now before we move on to the next application, let me show you the insides of a typical op-amp that we use as a comparator, LM393. You can see the inverting input terminal over here. Non-inverting input terminal is over here. Don't worry about how complicated this looks. Everything looks complicated when you don't understand it. Later in the lecture series, you will see that this is not as complicated as it seems to be. Right now, concentrate only on the output stage. You can see it is an open collector output. Open collector output is especially useful when you have to short final outputs. Let us now build a multi-level detector, which is a circuit that will tell you whether the signal is between different levels. For that, again, we need two op-amps. For both of them, input will be given at the non-inverting terminals. For the reference voltage, again we'll take a voltage divider from plus VCC, and this time also we will have three resistors. To make it simpler, let us assume that R1, R2 and R3 are equal, and let us say plus VCC is 9 volt. Plus 9 volt will be divided between three equal resistors. So here we'll get plus 6 volt and here we'll get plus 3 volt. For the first op-amp, reference will be taken from here. For the second one, it will be taken from here. Let's take V1 and V2 as the individual outputs. Finally, we will connect three LEDs like this. Here we give some plus 5 volt and here we have 0. Let's take a table. In the first column, we have the levels of input. Input can be less than 3 volt. It can be between 3 volt and 6 volt. And it can be greater than 6 volt. Take the first case. Input is less than 3 volt. For the first op-amp, reference voltage is plus 6. When input is less than 3 volt, input is less than 6 volt. That means output will be negative Vsat. For the second op-amp, if input is less than plus 3 volt, which is its reference voltage, output will be negative Vsat. In the second case, input is between 3 volt and 6 volt. Input is less than 6 volt. So for the first op-amp, output will be negative Vsat. Input is greater than 3 volt. So for the second op-amp, output will be plus Vsat. In the third case, input is greater than 6 volt, which means input is also greater than 3 volt. So output of both op-amps will be plus Vsat. Let us now see what happens to the LEDs in all these three cases. In the first case, V1 is negative Vsat, V2 is negative Vsat. The green LED will have plus 5 on the P side, negative Vsat on the N side. It will be on. Yellow one will have negative Vsat on both sides. It will be off. Red one will have negative Vsat on the P side, 0 on the N side. It will be off. In the second case, V1 is negative Vsat, V2 is positive Vsat. Green LED will have plus 5 on the P side, plus Vsat on the N side. Plus Vsat is plus 9 volt, so it will be off. Yellow one will have plus Vsat on the P side, minus Vsat on the N side. It will be on. Red one will have minus Vsat here and 0 here. It will be off. In the third case, V1 and V2 are both plus Vsat. Green LED has plus 5 plus Vsat. It will be off. Yellow will have plus Vsat plus Vsat. It will also be off. Red one will have plus Vsat 0. It will be on. This way, the circuit will show whether the input is less than 3 volt, between 3 volt and 6 volt, or greater than 6 volt. Now before we move on, I want to draw this circuit also in such a way that input is on the left side and output is on the right side. Let us now make a time marker generator. It is a circuit that produces sharp, narrow pulses at specific instants on a waveform. Let us make one that marks every time the input signal goes above 0 volt. For that, the first thing we need is an Opamp. We'll give the input at the non-inverting terminal. To mark whenever the signal crosses 0 volt, we'll give the reference voltage as 0. Let's call the output V1. What we have is a non-inverting zero crossing detector. Let's take a sinusoidal input signal and plot the output V1. It will look like this. Every time the signal crosses 0, output changes the state. Now, this output will be fed into an RC differentiator. Let's call the new output V2. V2 will be derivative of V1. We already have plotted V1. Let us plot V2. It will look like this. We have a positive pulse every time V1 goes from negative to positive. We have a negative pulse every time V1 goes from positive to negative. Now this output will be fed into a clipper. Output of the clipper is our final output. We used a negative clipper, so the negative portion of V2 will be cut off. The final output will look like this. We have a sharp, narrow pulse every time the input signal goes above 0 volt. So that's all about it for today. See you in the next lecture. And please don't forget to subscribe.